Assalamu alaikum and good day everyone, and thank you for joining us today. So today we are excited to present the findings from our experiment on the fabrication and characterization of p-n junction diodes and diffused resistors. So these devices, yeah, they are crucial for performance of various microelectronic applications, including rectifiers, signal modulators, so on, so forth. So our presentation will guide you through the fabrication processes involved and the characterization employed to assess the electrical properties of these components. By the end of the presentation, we aim to demonstrate the importance of precise fabrication. So let's dive in and explore.
Okay, we're using a P-type as our substrate. The orientation is 100. The diameter of the wafer is 525 micrometer. We're using the RCA1 to cleaning, remove a particle on the wafer. Okay, next is the oxidation process. We place our wafer into the furnace with the control high temperature to the grow silicon oxide. We measure the silicon oxide thickness at 5 different points and we got the average at 3725 Armstrong. For photolithography process, we define the active region using mask 1. We apply the photoresist on wafer and then we spin coat it for 500 RPM for 6 seconds. And then we're doing a soft bake. We soft bake it at 60 degrees Celsius for 60 seconds in purpose to semi-harden the photoresist. Then we align the wafer with mask 1 before we expose. We expose the wafer using the UV light for 10 seconds. After exposure, we develop the wafer in the developer solution. And then we hard bake the wafer at 90 Celsius to fully harden the photoresist. After hard bake, we're doing inspection at power microscope to see the photoresist layer and the silicon oxide layer. For the etching process, we etch the wafer using the buffer oxide etch to crease window for the diffusion process.
Right after etching, we diffuse phosphorus into our wafer. So, wafer is placed in furnace at 900 Celsius for 30 minutes with phosphorus gas.
Then, we regrow the oxide to insulate active area before our next photolithography process. The thickness silicon oxide on silicon measure are to be 3112 Armstrong, where as the thickness of a silicon oxide on silicon oxide is 4985 Armstrong.
Then, we did a photolithography process again to define contact card using mask 2. Same steps were repeated but this around with mask 2.
Then we did the inspection of our wafer after etching is completed. As you can see, contact card M plus on diode looks at the first picture. Same goes to the other picture in the right side is a contact card M plus on the resistor. Moving on to the final process which is metallization. So the wafer will placed in the PVD chamber and the aluminum is deposited through evaporation at 660 Celsius which is melting point for the aluminum wire. Then we do the same photolithography process to define metal layout using mask. So right after we did that, the PR will remove using acetone and we clean our wafer using the water to remove any contaminant left. Finally, we did the electrical testing on resistor and diode fabricator of our wafer using spectrum parameter analyzer to define IV characteristic.
Alright, now let's talk about the results we managed to get. The first resistor result was not bad at all, since the IV demonstrated a linear relationship, but the resistance reading were quite huge though. It was around 3 by 10 to the power of 11 ohm. The current observed were in femtoampere, since the resistance was that high. And yeah, to be noted, this resistor had the largest distance between contacts, so theoretically, it should own the highest value of resistance. Let's see if the other resistor surpasses this value. Now, the IV for this resistor looks a bit messed up at higher voltages. It showed sign of linear relationship at low voltages, But as voltage increases, there's a sharp rise in current, and yeah, it gets worse over as the voltage grows bigger. So possibly it's breaking down at higher voltages. The good thing is these resistors contacts were closer, so the resistance should be lower than that of the first resistor. And yes, it is, with the value of 8 by 10 to the power of 10. Third resistor looks messed up, to be fair. It started off in linear manner at lower voltages, but as the voltage grows, the IV is going out of control again. But yeah, this resistor had even closer contacts arrangement, and the resistance were lower with a value of 3 by 10 to the power of 9 ohm.
This is what our fourth resistor IV looked like. So calculated resistance was about 2 times 10 the power 11 ohms. Doesn't resonate with our theory where closer contact spacing in resistor should produce smaller resistance value. So from the graph itself, we could see a nonlinear behavior like fluctuation in current at all points of the graph, which could indicate that the resistor is not working at all. Unfortunately, even though our IV characteristic looked like ideal resistant IV, this fifth resistor had a resistance of negative. Speaking logically, there is no negative value on resistance. So, positive current should have been observed as a voltage increase following Ohm's law. It is suggested a non-ideal behavior of resistor. Moving on to our first diode, which had a larger diffusion region, the threshold was about 3.5 volts to 4 volts, which is way much higher than typical 0.7 volt threshold voltage of diodes. The forward bias behavior shows a gradual increase in current as opposed to exponential increase the we usually find in the normal diode, which could indicate there is higher series resistance or could be because of poor junction quality.
Knowing that, we examined the second diode. Its IV graph characteristics appeared irregular. At negative 2 volt, a gradual current increase was observed, which was identified as the diode's threshold voltage. This value is unusual for a silicon diode. In forward bias, the current rise after the threshold voltage was gradual rather than the typical sharp exponential increase in normal diode. In reverse bias, the behavior showed minimal reverse current, indicating the absence of reverse breakdown. Next, the IV graph characteristic of the third diode was analyzed. The threshold voltage was observed at 3.3 volt, which is higher than expected for a silicon diode. However, this diode demonstrated an exponential current rise in forward bias, resembling the behavior of a typical diode. In reverse bias, the negative current remained low. Notably, there was a gradual current rise even before reaching the threshold voltage, deviating from the flat region typically expected in a standard diode IV curve. The fourth diode shows IV graph characteristics similar to the third diode, but with a higher threshold voltage of approximately 5 volt. Finally, the analysis of the fifth diode revealed behavior that deviated significantly from that of a normal diode. There was no distinct threshold voltage, and the current displayed a gradual rise instead of an exponential increase. At higher voltages, the current rose steadily, resembling the behavior of a resistor.
Based on the IV characteristics graph from the previous session, we have has a discussion about the issue and came up with a few solutions. Okay, for the first issue is the high threshold voltage in diode. Typically, the ideal diode will give us the 0.7 volt threshold voltage, but from the graph, we get the value about 3.36 volt until the 5 volt. The problem you can see from the image that the low doping concentration and medium doping concentration cause this issue. So the solution is we need to increase the concentration or improve the junction quality. For the next issue is the gradual increase in the current before the threshold voltage. So basically the current increase gradually before the threshold voltage instead sharply rising after the threshold. So the potential cause is the high series resistance, low doping concentration, and fabrication issue during the lab. So the solution is we need to reduce the series resistance value and ensure proper junction formation. Our third issue, which is the incomplete aluminum deposition and etching issue in contact. So basically, like in the image, there are a few defects in metallization. So this problem will cause the issue like incomplete aluminum deposition and give us a less precise value during the IV characteristic graph. So how we can solve it is by review the deposition parameter again or improve the etching contour so it will not undergo over etch or under etch. The fourth issue is the overall device non-idealities. So basically non-ideal behavior such as gradual current increase and non-linear behavior indicate the issue in the diffusion region on series resistor. So this is caused by the fabrication imperfection step may be caused by our team. So the solution is we need to optimize diffusion and doping process and improve the process control.
In conclusion, we successfully fabricated and characterized p-n junction diodes and diffuse resistors. Through the characterization of the IV curves, we observed that while the resistors generally followed the expected behavior, we encountered unexpected results such as breakdown at high voltages and then gradual rise in current before threshold were reached, and then gradual rise in current as opposed to exponential rise after threshold and so forth. This deviation suggests that some of resistors and diode exhibits non-ideal behavior, likely due to fabrication issues such as improper doping, shallow diffusion, or contamination during the manufacturing process. The results highlight the importance of precise control in fabrication process to ensure reliable electrical performance. Future improvements in process control of fabrication will help address the non-idealities observed, ensuring more accurate and predictable behavior of the devices. That's it from us. Thank you.